So now, and I had some questions from a few of you regarding the labs, especially if it's necessary to do the labs, if you already did them in the previous semesters. And the best advice I can give you is that there will be questions on the written exam from the labs as well. So they are part of the syllabus. And obviously, if you don't do them, then even if you're allowed to take the written exam by the exam office, it will be much more difficult for you. And there was also some question from two students regarding if you can take this course remotely. And in general, you cannot. You need to attend the university for the labs and the lectures. But currently, everything is digital. So as long as the university is closed, we can follow by digital only. But once the university opens again, I am not sure if I will be able to provide a recording to YouTube of the lectures or not. And also the TAs, they will primarily only be approving labs on the university itself, unless you have a special agreement. Yes. So one more thing, if there's any questions in the lecture, then you are free to just interrupt me at any point. And if you prefer not to speak, then just write the question in the Discord channel, because when I'm presenting here, I cannot see the Zoom chat, so it's better to post the questions in the Discord. So, okay. Yes, the first introduction, the first subchapters in the books, they are in chapter 2, they are talking about abstractions, and mainly in this book, it will be two abstractions that you will see in all the algorithms that are presented, and that's processes and links. So processes, this can be anything, as I talked a bit about last time. It can be from on computer itself, or a virtual machine, or also just a specific part of a thread or an algorithm. So the actual description of the algorithm will make it more clear what's a process. But for the abstraction, it can represent anything. And the links which they are using in the book, this is just a way for processes to communicate. So it doesn't talk about if it's a Wi-Fi network or a cable network or whatever. Just there's a way to communicate by sending messages between processes. And then there is a third abstraction that is used. This is regarding failure detectors. So this is a thing which abstracts time, but this is also yeah, you're supposed to see my screen. Okay. So Yeah, maybe I started the recording but not the screen sharing. Okay. Good to know. It is difficult to have things on digital only. So now, what screen are you actually seeing? My background. Yeah, so hopefully now you can see the slides. Yeah, great. Yeah, sorry about that. Anyway, I was just on the second slide here with the three abstractions, and yeah, as I said, the first two are the main ones that is present in all the algorithms pretty much, and then there's also the failure detectors, which captures the failure, obviously, of a process or a leak, and when it says time here, it captures the timing behavior. It means that you can think about when a process crash, its clock stops. It stops to do anything. So this is and also that if it's performing very slowly, then its time is sort of stretched out. But yeah, let's get into the more details about the processes. So in all algorithms in the book, unless it's specifically stated about reconfiguration, it has a finite set of members, meaning that before the algorithm starts, or the execution starts, you already know about the participants. So this is typically if you have a consensus algorithm, for example, Paxos, which we will discuss later, you already know beforehand how many processes will be participating. And this doesn't change either by people or processes leaving or joining, unless it's specifically stated. And we often refer to this as the cardinality or the size of the group. And the processes, they communicate by simply message exchange, and the processes, they are always uniquely identified. So when an algorithm is described, there is hello? Was there a question? Oh, I heard some. Yeah, so they are uniquely identified in the algorithm. Then the book talks about how we can, or what happens inside a process itself. So the abstraction is that there is a internal clock tick inside the process, and in each clock tick, in each clock tick, it does one action. So the actions, it's either to receive the incoming message or to process the message or to send it out on the channel. So this is one step of the process. So the communication, this is the latency of the algorithm. And when we are talking about latency in these sort of algorithms, it's always how many steps does the latency represent, because we don't have any notion of seconds or milliseconds inside the algorithm. So it's just about how many steps. Yes. So this is another figure of what's the three main process steps of a system. Yeah. So in all algorithms, especially those concerning consensus, they will talk a lot about liveness and safety. And this is a very important thing to be familiar with, because yeah, you will use these properties to classify algorithms, and also later on reason about which algorithms you will use. So the safety, this means that the algorithm doesn't do anything wrong, and the opposite, or the other property, liveness, this is that the algorithm does something useful. So if you have a system that has only one of these properties, then it's not really useful, because for example, if you have a system that is always safe, then it might never do anything, because the only property it provides is that it will not do anything wrong. So the easiest way is obviously never to do any action. And for liveness also, that if you have a system that just does something, it might do a lot of mistakes or wrong computations. So the caveat here is that obviously you want to have both, but surprisingly, this is it's impossible to guarantee this. So what happens is that you have a what we call an eventual liveness, or yeah, usually eventual liveness, meaning that if for example, the system crashes, then it's obviously not live because it's not doing anything. But if it recovers later on, then we can say that the system is eventual live, or eventual liveness. Yeah. So we will see more of these properties when we go into the consensus algorithms. Then probably if you took the database course, you will have heard about this, maybe also in the data-intensive systems, the CAP theorem, consistency, availability, and partition tolerance. And we also use this, or we can use this abstraction to describe systems. And again, here this is similarly to the safety and liveness, only that in this case we have the theorem states that it's impossible to have more than two of these properties simultaneously. And this is important to highlight the simultaneously here, because it's often misunderstood that you can have only two of these properties, but you can have all three, but just not simultaneously. So this means that, for example, if a system, or we can see in this graph here, or figure out that if your system is consistent and available, it can be consistent and available at all times, but it can only handle partitioning, or if it handles partitioning, it will not have these properties during this time. So, this is like that if parts of the system goes down or is partitioned, then while this partition happens, the system doesn't provide two other properties because it's simply unavailability. But once the full system is restored, the other two properties are guaranteed. Yeah, so the process failures that we will have in the course, they are these 5. Mainly we will have the number 1, 3, and 5 failures, meaning crash failure, crash with recovery, and arbitrary. And you need to, when analyzing an algorithm, you need to be very clear about what kind of failure model are you analyzing it under, because to handle these different types of failures, this will affect your algorithm a lot. So, for example, the crash failure, this is the most easy way that you can have a failure. It just means that your algorithm is executing, and at some specific time it will crash, and then afterwards it will never execute any computation again. So when you assume that a process is always correct, this means that it will always be correct. So in this failure model, if you, for example, have 3 processes and one crashes, this means that after it crashes, there will just be 2 left, 2 correct ones. So it might crash from any of these 3 computational steps, from processing the input message, or from the executing the algorithm itself, either something with the state or the logic or the configuration, or it might crash when sending out the result. Then we have the omission failure, which is it will not really be used so much in the algorithms in the books, but you should still be clear about this. So this means that it commits to do something, like if it's supposed to send or receive a message, it doesn't do it. So this is more specifically with the input domain or the result domain, that it doesn't crash in the system itself or the algorithm itself, but it omits to do something. And then we have the commission failure, and this is the opposite, sort of, that the algorithm does something that it shouldn't have done. So that can be a failure where a process can send a message that it wasn't supposed to send. And obviously this can cause big problems. Crash with recovery. We will, or you will see this in your labs, and also you will see why this isn't supposed to be so easy that you might imagine. This is because when a process crash, it might also lose the internal state that it had before crashing. So its state, here we are talking about its memory, let's say. So if it has done some computation and afterwards it crashes and it's brought back, then it's brought back without any memory or without its state. So there is obviously ways to fix this by using a persistent storage, for example. Then it can be brought back with its state that it had before. But still, you can have issues with if one process crashes, the other processes can continue running, and the crashed processes doesn't know about what the rest of the system did while it was offline. But yeah, the book will also talk about this failure abstraction. Then we have eavesdropping, which is more and more relevant, I will say. That a process might leak information somehow. So this is, you can imagine, typically a hacker has gained access to your system, and then it can read information from this process. Okay, low voice. Okay, I will try to move my microphone. Okay, just say now I moved it 1 meter closer. So just tell me if it's any better. Yeah, great. Yeah, so the eavesdropping fault. This is typically handled by some kind of cryptography or network administrator or something like that, but it still might be a fault in the processes itself or the algorithm itself if there is any way to retrieve information that should be kept private. And then we have the most broad and most interesting failure abstraction, which is called arbitrary. And in this model, typically there is not made any assumption of the failed process. So this abstraction sort of captures everything else where the process can do anything, and this can be that both that they do something bad because of a hardware failure, for example, or a system failure, but also if there's a hacker that's been able to access the process and it captures everything that this malicious hacker could do. So obviously this is difficult to handle in systems, and there isn't many algorithms that can handle this sort of behavior. So when Bitcoin came, this is a lot of people consider this as the first algorithm that was really put into widespread use, where you have a system that handles arbitrary failure, or because in Bitcoin, obviously anyone can try to do something to break the system, but somehow it's still running. So there was things or systems before that, such as PBFT, which we will talk about if we have time, but it wasn't put into widespread use, such as Bitcoin. So the in the literature, you will also see this called as Byzantine, and the reason for this is that it was first described using a sort of I don't know if it was some Byzantine army that was trying to attack a city, or if it was an army trying to attack a Byzantine city. But anyway, the problem was that there was one general and two lieutenants, and they had to, or they wanted to attack this city, but it works so that only the attack would only succeed if all of them attacked at the same time. So if either one or two of the general or lieutenant attacked, then they would fail, and the city would win. So the problem is that how will they coordinate this attack? So if you imagine that the general tells the two lieutenants to do an attack of the city, but one of the lieutenants is malicious, and he tries to convince the other lieutenant, the lieutenant one, that the general told him that they should retreat. So in this scenario, there is no way for the lieutenant one to know who is being truthful, and so either he has to trust the general, and by trusting the general, he might risk that he is attacking by himself, and or if he is trusting lieutenant number two, he retreats, then yeah, he risks that his army will attack without him. So this is also not good. And there's also that the general might be malicious, and he can try to he can send one message to one lieutenant and a conflicting one to the different lieutenants. And again, there is no way for the lieutenant one to know who is speaking truthfully. So it turns out that there is no way to solve this this issue when you have just three participants. So it turns out that the only way that you can solve this is that you must have a fourth member. You must have a third lieutenant. And once we go more into the algorithms itself with quorums and these things, then it will be more clear why this is. But here, even though the general is sending one message to lieutenant one and a different one to lieutenant two, due to that they have a quorum of lieutenants, they are able to detect that the general is lying, and thus they can say that he is not trustworthy, and they will not continue with the attack. So that's the abstractions that we will have regarding processes, and then we will have some cryptographic abstractions. And I guess most of you had a cryptographic course already, or computer security or something of the sorts. But in this book, it's also very relevant with the hashing function, especially, and the digital signatures. So I will just go through them. So you know the main concepts. So the hashing function, or the cryptographic function, it's used in our domain as a way, as a one-way function. That it's easy to make the eggs into an omelette, but it's really difficult to try to make eggs from an omelette. So it has these properties that it's a one-way function, that you can take a long or any variable length inputs and pass it through the hashing function, and you will have a fixed size output. But there's no way to take the output and retrieve the original input. And then there's also the properties that you cannot find a different input value that has the same hashing value, and also that you cannot find a collision between two, which is a different property. Then the message exchange authentication codes, which are based on symmetric cryptography. This is heavily used in Byzantine fault-tolerant algorithms, because it allows or it can prove to you who sent the message. Because if you see here that every process, they have a matrix, let's say, with the max that they will communicate with the other processes in the system with. So every time that they want to authenticate a message, they pass in what process they are, and who they want to send the message to, and then the message itself, and then they will generate a authenticated message, or a encrypted message. And then once this message is sent to the receiver is able to decode this message and get the original output. But the main weakness with this scheme is that you need to have a lot of symmetric keys. And you can imagine if for example, Bitcoin tried to use this scheme, then it will require you to store thousands of encrypted keys for every participant that joined, and it's just not practical. And the second weakness is that there is no way to prove to you who sent the message. That you encrypt something with a key, and then it doesn't really prove to you that or it's difficult for you you know who sent you the message, but you cannot prove this to a different entity. So the abstraction or the different solution to this is that we have digital signatures, which is, or you can imagine that this is sort of like Max with the public verification property added. So digital signatures, this is based on asymmetric keys or public and private key pairs, and it has pretty much the same properties as the hashing function, just that here in the literature they usually give them a different name. But again, the main thing is that you cannot given a message, you cannot retrieve the private key back. Yeah, on the next slide it will be more clear that you take a message and then you encode it with the private key. Then you sort of send the message plus the signature that you generated together, and the receiver is able to see that if he uses your public key, this message will match the signature. Since this public key is public, then you can assume that everyone knows this key, and also this means that anyone can be sure that whoever sent this message, he must have the private key which is associated with the signature. So yes, that's it. So is there any questions to the first 3 subchapters? Because I was thinking that we will go into the next on Monday, the next subchapter. So if there's any questions about this, we can take this now. And if there's no questions, we will take just a 10-minute break, and then we will go into the Go tutorial. Okay, I don't see any questions, so let's meet 9:15. And I'll try to put up a timer. No, Okay, so let's meet in get 7 minutes. All right. Hello all. No, okay. We are 1 minute late. I'm 1 minute late. That's it. Okay. First off, is there anyone that has any issues now with the labs regarding the setup of Unix account or something like that isn't been resolved yet? I know there were some people that didn't have access. Getting access denied. Okay. Let's see. For me. How is it possible that Zoom consumes all my processor? Doesn't sound so great. Um, yeah, might be the recording not so strong machine maybe. Anyway. Yeah, Øystein. Okay. So you're the only one that have access issues. But you only need the Unix account to generate the token. So you can work on the other parts of the lab until it's fixed. Account issue. Okay. With regards to the Go tutorial, I thought I would just go through the tutorial that's posted on the golang.org webpage. And yeah, as I said, if you're already proficient in Go, then you will maybe not have so much new information here. But anyway, if you like, you can just open this page yourself and follow along. I think some of these on this tutorial, they have some small tasks that you need to do, and then you can reset or run the code in the down right corner. So this is the very basic hello world, and what does it have here? It has a main function, which is what's the main entry point of your application after it's been compiled. And then it has the import FMT. This is a library which has the print function. So anytime that you wish to print something to console, you need to import FMT first. Otherwise, not so much interesting going on here. So let's see, what more do they have? I wish my similarly, if you need something with time, import time, you will have a function or a library that has a lot of functions that allows you to play with time. For example, you need to calculate time, or you need to run benchmarks, perhaps. So this is a library that you can use. Time. Yeah, we already talked about packages. For random, you can use this one. I think it works without math also, but not sure. Okay, no, it should be math / rand. Yeah, square root. Functions defined like this is usually opposite if you're used to programming in C or C#. They usually have the data type first and then the variable name, but in Go they have it the opposite way around. But also this allows you in Go to remove the first or all the data types that are of the same type. You can put them like this, and I can put I can have if I had more. Now I changed this function to have 6 input arguments, and they're all type int. So yeah, obviously it will not run because I didn't change my function down here. But yeah, once I pass the number of arguments, you can see that all the ones is got as int, and the return type, it will be at the end. Yeah. Then in Go, it's very easily to return multiple values of a function. So, for example, in C#, you cannot do it this way. In C#, at least, maybe not the latest release, but previously you had to use a tuple. But here in Go, you can very easily return any number of arguments, and they don't need to be of the same type. You can also have that I want to have, for example, 2 strings and a number, and then I will just add whatever I want. But in Go, you always need to to do something with these arguments. So I can define a new variable C, and yeah, I can try to print this underneath her. So now you see that it prints number 8. But in Go, if I say that no, I will just receive this parameter and then I will not do anything, Go has this issue that, or not issue, but this safety feature. Let's say that it will not compile if you have variables that you don't use. So when you're developing, a very quick thing to do is that you can use this special underscore character. And you just say underscore equals C. And then this is sort of a trick to say that I don't care about this. And you're also allowed to do this on the when you're executing the function also. So I can say I will take a, b, and then I have underscore, which I don't care about. So this is what you will typically do. Yeah, and then you can name your results as you see here that it has using these x and y variables, and then it just hit types return at the end of the function without saying that it wants to return what numbers, but it's this is great. Variables, yeah, you know about variables. Can initialize them. Great. Yeah, different ways to initialize. Yeah. You have the normal types in any language, string and bool, int, and uint. Okay, so one important thing with Go, especially, is that you will need to do a lot of type conversion because if a variable is an int, it can only be used to function that takes int as an argument. If I try to put an int into for example, this square root function, it will not allow me to do this. So if I type x, y here, it will say that it's not legal. Also, it wants just one variable. But yeah, it says that I cannot use int as a float. But I also think that you cannot type float here. It will say that it should be of float 64, but I guess they have 32 also. Yeah, so you cannot use a type 32 as a 64. So it's very important that you typecast to the correct type. And you do it that you're sort of calling this type as a function, and then it will return the type that you want. So you can change a type, but why would you ever do that? Pretty much. Constant, it's not so interesting. Constant. Yeah, we define constant as here, but
that's this lesson. Let's see if there's more interesting. Okay, so a for loop. This is pretty standard C syntax, but there are some interesting things here that, for example, you can define not only one variable initially. You can have two, and also in the yeah. So this is the three steps or the three things when you set up a for loop. You have the initial conditions, then you have the invariant, and then you have what happens between each step. So you know, 99% of the time you will see this I++, but you are allowed to change this to stuff like this, for example, that you can say, you know, that I want to increase both I and j, and then you can, for example, print in every execution. So yeah, so the exit form probably that should be like this. Yeah, so now you see that I'm printing j on every step, and it's increasing, and also at the end it's showing the sum, which is just j. So I hope they will get into a while. Yeah, so here you have something which is you're more used to as a while loop. In different language, this is usually called a while loop, but here in Go you don't have a while loop, you just have the for loop, but you're sort of using it as a while loop. So I think even it will allow you to remove these semicolons there. So it's printing the same value as if I had them. So anytime that you want to use a while loop, you will just type a for. Pretty easy. Okay, this was actually the next slide here. So you will see this a lot in the code in the labs. You have a forever loop. Something runs forever. You just do like this, and this is one way that you can keep your program running until some specific condition is met. If statements, they are without the parentheses, and you always without the parentheses around the condition, but always with the parentheses around the conditional execution, or what's the correct wording? But this is just syntax things. One thing Go allows you to do is you can initialize a variable in the first part of the if statement, and then you can evaluate it afterwards. So here the v variable is initialized. So yeah, I guess we can try to do one exercise here. Yeah. So it wants us to run this 10 times. Just declare set equals 1. We can have a simple for loop running 10 times. This is the formula. Okay. Now, needs to be the correct type. Okay. Important step. Okay, so let's say square root of 9. 3. Okay, so this approximation formula works great. Not so difficult. Switch statements, you know about this. Nothing special here also. By the way, if there's any questions, we can take them now, any programming related questions, or you can ask the people in the lab, the TAs. Okay, so here comes one interesting thing finally. So this is defer statement. So what you can do in Go is that you can write a defer and then you can write any function afterwards. And what this will do is that it will execute after the function. So if I run this, it will print hello, and then main function will terminate, and then it will run this hello world. So I think that there is a stack which that it's put into a stack. So if I do like this, that I defer this and then I defer this, probably what will happen is that this one will execute first and afterward this one. We can see. No, it's the other way around. So this is put at the bottom of the stack and this one is on top. Yeah. Okay, so it's like a stack. So that's typically you will use this to close a file, for example, that you opened, or to send something on a channel, or because even if the main function had crashed out, then this statement will be executed. In C-type language, they use, or C# at least, they use a try-catch pattern to do this thing many times, that you want to run something at the end, even if there's a failure. Yeah, last in, first out. Okay, pointers. I hope that you're all familiar with pointers, because they will be used throughout all the labs. So it uses the same syntax as in C to use the ampersand to point to the address location, and then the asterisk to dereference the pointer. So if I set p to ampersand e, I will point to the memory location of the I variable. So now it prints the value which is located there, which will be 42, and then since p is pointing to the same memory location, I can change the value. So first it's printing the value of 42 of I, then this line is changing actually the variable I. So this is and then it's printing here 21. So this is something that you must be comfortable with to solve the labs to pointers. Yeah, and also with structs, which is kind of similar to a class in C#, if you're used to this. Just that it doesn't have any functions here. It's just a set of variables that belongs to this struct. So I can also here they have a vertex with x and y points. But you will see that much more complex structs will be used in labs. For example, for each of the roles in Paxos, we will use a struct to represent each of them, because each role has a set of or a lot of variables that it needs to keep state information. Let's see. Yeah, so you can point to structs the same way that we did previously with basic data types. So here it's creating a variable v, getting the address of that, then it's changing the x member of the struct. So it should print 1 billion and 2. Yeah, more on structs, something we didn't cover. Arrays, obviously also data type that you will run into. It works similar to different languages if we are talking about an array, but in Go usually you are working with what they call a slice, and it's almost indistinguishable when you are working in your code what's a slice and what's an array, so you don't really need to worry about that, I would say. It's just with the slice abstraction, it allows you to do, for example, these things here that it's creating a array here with 6 numbers, and then it's you're using this as a slice and retrieving the elements 1 to 4. So the S, it will be a slice of the 1 to 3, I guess. Yeah. So the first index is this one, and then this. So if I change this to 0, it will also retrieve the 2. And you can do some nice things here that I can say I want 3 colon, for example, and it will just retrieve those the three, not the three last ones, but I will get, I will skip the three first. I will take from 3 and out. And you can do this so that I want up to number 3. So I will get this, I guess. Yeah. So I will get everything up to number 3. And if you want, for example, to get the last one, you can do something like primes. So now I said that my length, I know that my length is 6, but I want to get everything from, yeah, I guess it should be like this. Yeah, I mean, it's so easy to make mistakes, but yeah, you take the length, which is 6, and then I subtract 1 because it's 0 indexed, and when I run this, yeah, I will have the first elements, and if I want to have only the last one, I will do it like this. So now, no matter how big my array is, I will always get the last one. So this is typically very useful thing. And yeah, if you want to get the first one, you can do something like that. Yes, so definitely useful thing to know about. Yeah, okay, sure, it shows more examples like that. Yeah. Okay. Okay, so they have this length and capacity thing here that you can keep in the back of your mind, I guess, that the capacity, this is sort of how much space is reserved in memory for your slice, and the length, this is how much data did you fill. So every time that you grow the capacity of your slice, it needs to copy everything and move it to a different memory location, which is larger than it was previously. So here I'm, even though I'm removing the elements, they are still in the memory, because I set my slice to not have any elements, but I didn't change the memory location. So therefore I'm able to extend it again afterwards, and magically they reappear. So it's clear how that you didn't change the memory address of the slice. Yes, and here one nice thing about slice is that it's easy to forget about it. Even I forget about this sometimes, because when what you do in typically C#, that you will write something like this. that you will say that if the slice is empty, is nil, not initialized, and the size is 0, then you will do something. Because if you try to do something like this in C#, it will tell you that you cannot check the length of a slice because it's not initialized. But in Go, you can check the length directly, even though yeah, now I probably messed up. So you can check the length even though it's not initialized or anything here. This is kind of cool. Yeah, and if you want to create a slice in memory that sometimes you don't know what values will be in here, then you will typically do it this way, just with you say what data type you want. You want a slice with ints, and then the size that you want 5 elements inside. This way here, this is for special needs that you don't need to do this syntax. As you will see, this just creates the same size of the slice with the same capacity, just that you're not initializing the values. So in the first scenario, you're initializing every element to be 0 because this is the default value of an int. But in the second case, you're not doing it. So in general, you will just use this way. But if you're very interested, you can also just initialize a slice with 0 length, but with the capacity reserved already. So with this different option, will be more high performance if you know that. I know that I will have a big slice. I need a big slice, for example, with 500 elements. Then it will resolve this in memory already. So yeah, 2-dimensional slices, for example, to create a board or a matrix or something like that. Yeah. So here comes the reasoning why you will, or you can initialize a slice with a bigger capacity. Because when you're calling the append function, which means that you're trying to add something to the slice, you can run the example here. But yeah, first it's initializing the slice or setting up the slice with 0 length, 0 capacity. Then it's appending one element to the slice. So what must happen here in the background is that initially it didn't reserve any memory for this thing. Afterwards you added one, then it reserved memory for 1 slot, or yeah, and then it does for 2 slots, and yeah, and here you see it's reserved for 6 items. So now it's we can have 6 here. So if I added 1, you see I have length 5, capacity 6. So if I add 1 more number here, it should say that it's like length 6, capacity 6. Yeah, length 6, capacity 6. And if I just add 1 more, we can see what will happen. For the number 9, for example. So now suddenly it has reserved memory for 12. So it like doubles the amount of memory that is reserved for this slice. But if I did it how it was described a few slides ago, that I set up my slice with the capacity 12, for example, or 7, then it wouldn't have to shift or move this instant in the memory. So it would be more high performant. Yeah, this is range. If you're familiar with C#, this is like for each type thing, that it's like going through all the elements in this slice here. So this is like a construct that it's not really needed in any time. You can just index it using the for loops that was described earlier with array indexing, but it's still, it's like kind of more nice, I guess, to do it this way. But it's just iterating through all the elements, so nothing too fancy going on. And yeah, as I mentioned before, that you're allowed to skip a value or use this underscore special character. So in the first case here, it's just returning the index values, index keys, and the second one you're ignoring the key, but you just want the value. So they yeah, I guess we can skip this exercise. Maps, very important construct that you will use a lot. It's called dictionary in C#. Then yeah, it's just like a hash table that you use the first type as the key, and then it can point to one element. So what's great about this is that it has very fast lookup time, because if you know the key, then it will be constant the time to find the type that you're looking for. So if we, for example, used a slice, we would have to go through all the elements in the slice to find the one we were looking for. But since we use a map, you can just input the key, which is Bell Labs here, and it will find us the vertex that we used immediately. Yeah, so you can initialize them. Very seldom I've ever saw that anyone did this, but you can do it. So what's this? Oh yeah, so this is to remove something you can use to delete. This will delete the key from the map. So here it prints 0 because this is the default value. But if you want to actually check that if one key is there, you need to use this syntax to get the value and then get this OK flag. Because you cannot just check if this is 0, because there might be an element with the default value. So you will use this syntax to retrieve the value, and then the special OK Boolean flag that will tell you if the variable is, or the key is in the dictionary. Yeah, so let's see, what do they want here? What's on the map? Count of each word in the string S. That's sweet. I don't know if these exercises are so interesting. Maybe it's just like for each word. Okay, never mind. You can split this. By the way, if you usually, for example, if you have a task like this, okay, here it links to the thing that you can use. But usually, what I do is just that I go to Google first, search with Golang, and then split string, and as long as you have the Golang search part of your search query, then it will usually send you to the Golang org. So probably we could do like split. And then we could probably do strings. All my bad coding skills from here. Okay, so we can cheat just with like one. Okay, we can keep going. I guess it is set this one. Then one more. Yeah, so this is what we should do. Yeah, okay, so we should say pure val and we can probably so I guess we can do it more elegant. Yeah, so what we did now is we took this word s, we split the string, as you see down here. I ate a donut, then I ate another donut. We created the map with the key int and the key string and the value an int. Then we just iterated through the slice that is returned by the split function, and we did just this increment here, which first it finds the word in the slice, so it starts with I, then it checks the map if this value is already present. And if it's not present, the value will be 0. We increment it. If it's already there, for example, it's 1, it will increment it also, and it will be 2, like we say here, that now it returns to us 2 because the string I is 2 times. So this is one way to solve this. But the main thing is that you should just, when you run into an issue, just Google Golang and then whatever thing you need, for example, the split, and you will go here and it will show you usually an example of how to use it. Okay. So we already saw functions. Okay, let's do this one. Yeah, so this one here, it's you're passing in a function to another function. So you're allowed to do this, that you can, you say that I will take as parameter a function that accepts 2 parameters of float and returns another float. So here I'm creating what is like an anonymous function, and this function is passed to the compute function. And also in Go that you can return a function, which is what they do here, I guess. No, they don't do it here. But so here, no, they are doing it here. Yeah, so it's returning. So this function addo, it's returning another function which takes in an int and returns an int. So now you are calling this adder with no parameters because it doesn't take any. Then you will have 2 new functions here, and here you see that you are using this function. So this push function and neck function, they will actually be this function that is returned by here. So this is something interesting to keep in mind. And one cool thing here is that since they have this notion of function closures, that you can use this variable here that was returned. So you see here that for example, the post function, it will be 0, 1, 3, 6, 10. So first it's with 0, then it says 0 plus 0, this is 0, okay. Then it will be 0 plus 1, it will be 1. Then it will be 1 plus 2, it will be 3. It will be 3 plus 3 is 6. 6 plus 4 is 10. So this variable is actually being used now for these two functions. So that's kind of cool. Way to do it. Not really so usual pattern. It works. Yeah, so you will, in the lab 1, you will implement Fibonacci, so I will not do this for you, but by so far that you have seen the tutorial now, they expect that you can do this quite on your own. Okay, so that's it. Let's take a 10-minute break and then we will continue with the rest of. Let's just see how much they have. Because I want to show you the channels at least. This is yeah. So now we already did 4 and we have 2 left. So let's take a 10-minute break and then we will do the 2 last ones. So I'll just put the timer. Okay, is everyone ready for the last part, the most fun part? Any questions so far about Go? About how to make a string, make an int, what's the slice, what's function, what's return, no, what's a loop, anything? Because it seems every year we will need to every year some people take this course and they don't have so much programming experience from before. So if you feel that you don't have so much confidence in your programming ability, then you should try to seek help now while we are still at the start of the course. I don't wait until labs 3, 4, and 5 because it will be too much work for you if you're already behind. So if you feel that you need uh, more help on programming itself, try to do it now. Yeah. All right. So methods. So the way you can sort of have a similar behavior to classes in Go is to extend types with methods, and you do it this way, that you have a special receiver argument first, then you have the normal function signature afterwards. So this allows you that this function can access the struct or the type of whatever type you're extending. So obviously this means that in your main function or in whatever function that you call it this way, that you first create the struct with the parameters it requires, and then you can call any function or method that's defined on it. So let's see what more functions they have. So here they have they turn it a different way around. So here the apps function, it's a like a global function. It takes in the vertex as the parameter. But in the previous example, this was like the receiver argument. So the apps function was not global; it was only to this type. So yeah, that's the only difference there, pretty much. So let's see. Yeah, so here they have created a function on a float itself. So they made a special type called myFloat, which is just a float, but this allows you to have a special function for this. This sort of thing, I never really saw it in practice, but I guess the point is here that you can, if you try to use just a normal float here, it will not work, because first of all, this function is defined on this type, and my float, even though you're creating a new type just from this type. In Go, it doesn't understand this, or it doesn't compute. It still treats it as its own separate type. So, and secondly, since this float here, this is not defined in my package. It's defined in the map package. I'm not allowed to extend this. So this is why you would do something like this, that I'm not allowed to extend this, let's say, standard or base type float there. So I will just create my own, and when I do this, I am allowed to behave freely. So this is a common pattern that you would use, that if you need to extend a standard let's say type, you would just create your own with your own name, and it doesn't need to be a standard function, but it can also be that you're importing a library, like open source library, for example, and you're not happy with how it works, then you can use this pattern to change it. Very common pattern. Yeah. So pointers, I think we talked about pointers. Let's see what they talk about here. Scale is defined on pointer type vertex. Yeah, so yeah, okay, so it prints 50 if we don't have the pointer type. Supposedly it will not scale. Yeah, so if you want to allow changes to your type, you should use this pointer type here. Very commonly, people will just use this pointer type anyway, like a common idiom that they will just type this, but okay, there's a slight difference that you need to be aware of. But this is the type of thing that you will notice if you already came so far in your programming, then adding the last asterisk there will not be the biggest challenge. Yeah. So let's see, try removing the asterisk from line 16. Can you see why the behavior changes? Okay, so okay, it doesn't compile at all. Yeah, so if you remove this, yeah, so I guess that this expects a reference type or a pointer type. So if we remove this asterisk, we should also remove this one. And probably it will, yeah. Okay, this is just the same thing we talked about. Yeah, same. yeah, so some things to consider if you choose a value or a pointer receiver here. 99% of the time you can just use the pointer. Well, maybe not, but this isn't important for this course. This is more like programming performance. So, but yeah, for our purposes, it will work anyway if you just have asterisks in all the method declarations. Yeah, so let's see what more do they have here. Yeah, interface. This is one thing that you will face in the labs, because in the labs, typically, especially for 3 onwards, we will provide you with a basic interface for implementing the consensus algorithms, and we will give you like a shell of what we expect your solution to look like, and then you're asked to provide the rest of the code. So let's see, this example, they have a APSA, they call it. This is the name of the interface, and both of these types, my float and vertex, they implement this function apps. So this means that both of them are implementing this interface. So I guess they have a small detail here that is the pointer to vertex type that implements this, and it's the type my float itself that's implementing the apps. So yeah, so here they have this issue that it will not work like that. But maybe if we just change it to the pointer, it will work. Yeah. Yeah, so I don't know what's yeah, since the T type has a M function, it automatically implements this interface here. There's no, you don't need to write this in any special way that one type should implement another, or one interface yeah, should implement the interface. It just does this automatically behind underneath the hood. Yeah, so yeah, okay, let's see if we can go to channels. So this is one interesting thing in Go, because they have this thing called empty interface, which is just an interface with nothing there. And since any type must have nothing, at least nothing, then any type is also implementing this interface. And Well, what you can do is like stuff like this, that you can have a function and it takes in an argument of interface or empty interface. And this means that I can send an int or a string or any type I can send to this function here. So in different languages, yeah, you can probably do something similar. That you will have a function that accepts anything. But anyway, this is the way that you will do this in Go, and this type of pattern it can be helpful to you if you are, for example, having network communication between two machines or two processes, and when you receive data, you can you can take the whole thing and pass it to your deserialize function, and inside there you can do the deserialization, or you can, you know, have a message structures that is so that you should deserialize it, and then it can be another sub message inside. So this is a pattern that you can use for this types of things. Type assertion. This is yeah, probably what you would do in the deserialization example. That this is kind of like you're not typecasting, but you're like checking if it's of this type. So here I'm yeah, I'm like defining a variable I as interface with this data, and then I'm reading this variable as it was a string. And it will not allow me to, for example, this line, it fails because it cannot read the string as a float. But when I have this double parameters here, it will check for me, so it will not panic. Panic is the same as crash, let's say. Yeah, so it panics. It means that it doesn't know how to handle this situation. So this is why this one passes, because it has this OK thing, and this one it will fail because it cannot typecast this interface when it's a string to a float. So that's something you will also need to use later on. Yeah, type switch, same thing basically, just that you do it in a switch statement. So that you're getting like the type, and then you're saying if it's an int, you do this, if it's a string, or if you don't know, you do the default statement. Yeah. Stringers, you will use this already in lab 1, or I think maybe lab 2, that you will just define the method called string that returns a string, and inside here you will format the output of your struct. So this is like the toString function in different languages. Okay, let's skip this exercise. too easy for us. Errors. Yeah, you will see this in your apps. Let's go to the channels. Yeah, okay, I can briefly about buffers and streams. You will have this in lab 2 at least. So what is all this stream and buffer? Basically, you can think of this as at least how I imagine this is like there's something something big that you cannot fit inside your memory. It's too much. You can imagine, you have a very big file and you want to process through this file, but you cannot put the whole file into memory at the same time. So you can use this buffer approach, and then you just read, first 5%, and then next 5%, next 5%. So you will not at any point you'll have too much data in your memory at the same time. And this is also used when you have a communication between two processes, that the communication happens on a stream, so that you only receive parts of the total input at a time. So you interact with the stream through this read function, where you create first typically a byte array, and you say that, okay, I want to read bytes, and I want to read 8 of them at a time. So then you send in this buffer where you want to get your data. The read function will read the next 8 bytes, put them to your buffer, and it will return to you if there was an error, and also how many bytes it was able to read. So if we go to this function, we will see that first it reads 8 bytes with these numbers. These numbers represent the ASCII characters, by the way. So this is not something so fancy. And then afterwards it reads only 6. And this is because it has only 6 items left that it didn't read from the stream. And the next time it tries to read this for loop, it stops because it receives the EOF, meaning end of file error. So it will not, in this case, it will not change the buffer. But what's important to see here is that you have the buffer of 8 elements, and obviously when it's initialized, all of these are 0. So the first time I read, before I call the first read, I will have 8 bytes, and they will all be 0. After the first time, I will have these values representing the ASCII value, and the next time I read, I only get 6 back. So it means that I was able to read 6 new ones. And if you inspect carefully, you will see that for these 6 first, they are changed. But the last 2 here, they are the same as they were. So this means that you cannot naively just read your entire buffer every time. You need to use this counter function here, so that you know how many bytes was actually read from the buffer before you will print something. Because if we change the function to let's say, okay, I don't want this M. You will see that it has hello R, and now it says reader, and then I have some extra, 2 extra character cells, which is these 2 that it was still in my buffer. And you can play with this thing and try to see what will happen with different sizes, but this is the way it goes. Yeah. Anyway, on to the next one. Yeah. Okay. Exercise. We will skip it. Yeah. Rot 13. You will do this in your labs. Basically, rotate all the characters 13 times. It's like a very ancient cryptographic function that you probably know about. Images. This lab will not do anything with images. Let's skip ahead. Okay, now comes the most important thing here. I said that about all the things. But this is Go routines, or also in other languages typically call this a thread. And in Go, this is really so simple that you just type Go in front of whatever you want to run in a different thread. So as you see, if I don't have this Go keyword, everything is executed sequentially. So it will print world 5 times, afterwards hello 5 times. But if I have this in its own routine, it will start 5 of these routines immediately. It happens, very fastly, and afterwards it will execute this sequentially. So every time I run this, if we inspect it carefully, it will have a different outcome, because or it should have a different outcome. But because there's no guarantees of the time how long it takes for each iteration to run. So maybe it will be even more bigger difference if we have both of them running in. Yeah, I guess we cannot do it like that because it just terminates. But if we have a endless loop here, maybe. Okay. Doesn't work so well. Anyway, the point is that this is how you run in its own thread. Yeah. How strange it did work. My great example here. Okay. Yeah, let's go to more interesting things. Channels. Yeah, so as I said, when you start its own Go routine, it will sort of execute on its own, and this is great if you want to speed up your application, but many times you need to synchronize the behavior. So for example, in this example, I guess they are they have a sum of numbers, and they want to add them all together as fast as possible. So let's see if it works. Yeah. So let's say this this works. So what happens in this program? That yeah, you create your slice of numbers, then you create a channel, then you have two calls to the sum function, just up here. And this sum function, it takes in a slice of numbers and the channel. And the channel, it says here what type will be communicated on the channel. So on this channel, only ints can be sent and received. So this function, it's pretty simple. It just iterates through all the numbers and add them all together, and in the end, it sends the result to the channel. So you will see that this function, it doesn't have any return. It doesn't return any value. What it does is that it just sends the result to the channel. And this complicated always looks so scary, but only thing it does there is that it just splits this thing in two. So it takes like the first half and then the second half, and sends as it like cuts the slice in half and then sends this to the sum here. And then this line 18, it's sitting here and waiting for a result. So it will first it gets a value here, and afterwards a value here from this function here. Once there is something to send here. So you can think about this as the program is blocking here. It will not have any progress until both of these, there's something on both of these channels. And afterwards prints the value. So in theory, that if we keep executing this thing, then this X and Y should be flipped around in some cases, because there's no, there shouldn't be any guarantee that the first numbers are processed more fastly than the second half. But there's limited how interesting it is to keep running this thing. Anyway, so if I try to well, we can do some things to see what will happen typically when you program your channels. So if I say that now I don't want to have this in its own Go routine. Let's see, will it work now? Now it says, "Oh, deadlock. This is very bad." And typically, when you get this deadlock, you know, if you're not experienced in this, it can be take a long time to figure out what's wrong. But if we inspect here, what happens is that first I make this channel here. Then I send into this sum function. I iterate the numbers, and then I try to send something to this channel. But what's the problem here? The problem is that now I am sending a value to a channel, but there's no one that is listening to this. So that my program counter, like the program pointer, didn't reach this line 19 yet. So this is why that I cannot send something to a channel unless there is something listening. So there's ways to fix this. Obviously, we can put Go here, or we can turn this into a buffer channel. So if we turn this into a buffer channel, it will work, because now we are saying that our channel, it has a buffer of 2, meaning that the channel can keep 2 values without it needs to be anyone that can read this value. If I set this to 1, it will probably crash again. Oh, I need to just, yeah, because now I have just 1. But again, if you inspect closely, you see now it's crashing on line 18. Previously, when it was without or with 0, it crashed on line 17. And again, I can set to 3 or to 2. So this is one thing that you can do to solve it. The deadlock, but okay, let's say we need to use unbuffered channel. What can we do? Okay, we can do it like this. Go func. Yeah, now I am coding live, and usually it doesn't work so well, but let's see. Then we can try to keep our program running like this. Let's see. Line 25. Let's fix this. Okay, maybe I so if you have a tip of what I messed up here now. Maybe it's this one. Yeah, okay. So what I wanted to happen is this. Yeah, okay. It fails afterwards, but the point is that now it works even though we don't have a Go in front of this, because now now I'm setting up the listener. Like now I'm creating a Go routine with the anonymous function here that is reading from these 2 channels. So I start to read, and in the main thread I will send. So the deadlock here is because of this line here. Don't worry about that. But these are different ways that you can make your programs with channels work. The main thing is that you must avoid deadlocks because oftentimes the runtime will not be able to detect this. So what happens very often, especially with the Paxos implementation that we'll do in labs 4 and 5, is that you have the scenario like I showed before, that you have something that yeah, you have like this, that something is trying to reach from a channel and nothing is sending into a channel typically. So if I had something like this, yeah, now it's very nice because it's printing my errors, but what can happen is that if you have a slightly different code setup, then it will just be here and it will just stand to waiting. And one part of the algorithm, it will wait for something to be sent, and just on one line or two lines below, it will be the actual sending. So your program will be like stuck. And so whenever you're working with channels, it's good to try to keep things organized so you don't end into this problem. Yeah, we already talked about buffer channels. Yeah, the range thing. Yeah, they have an example here that if you have a buffer channel, for example, here you have 10 elements, then here I'm running the Fibonacci function, and I'm passing in this channel. This will run 10 times because this is the capacity. And then I can have this range, which is like just reading from the channel anytime there's a new value. So yeah, it just keeps reading, and it terminates once this line is called. So this is the close that you're telling that now my channel is closed. There will be nothing more sent to this value. Yeah. Select in Go. This is like a switch statement. You can think about this as a switch, but it allows you to wait for multiple channels at the same time. So in this case, I'm waiting for I guess the C channel, or I'm waiting to write something to the C channel, and I'm waiting for input from the quit channel. So in my function, I set up two channels. One is for C, probably like count off or result, and then a quit channel to tell to different parts of my solution that now I quit my program. So what it does is that it has a go routine with an anonymous function, and here it has a loop. So this is like exactly the same as the wage that we saw in the previous example. Just here they have written out the formal formal for loop definition, and for each iteration it's reading from the C channel, and once it's done all 10 iterations, it sends a 0 value to the quit channel. When we start this function, it's initialized with these two values, 0 and 1 for x and y, and then this for loop is running forever. It has no termination itself, and then it's trying to write x onto C. So it's trying to read to here, but remember it can only write to this channel if there is someone reading. So first it must the code will be stuck on this line. It's trying to read from this channel, and only then this algorithm is able to write. So it writes something there. Afterwards, it updates these two values, and it continues to the next iteration. And again, it waits until it can read, and then it writes. So it keeps going until 10 times. Then 0 is sent to this channel, and it reaches to here and prints script. So we can just see that it works, but looks good. Yeah. Yeah, default, same as a switch, like a default case. Okay, we can skip the exercises, or we can do them as homework. Okay, now we are at probably one of the last things here. This is locking, and also important aspect that you use this mutex, mutual exclusion, to prevent or to prevent concurrent access to critical parts of your program. So here in this example, they have, for example, what they call a safe counter, and yeah, I guess they are incrementing this, but they don't want that you will have many people to increment, because it can be you have like these dirty reads or inconsistencies in your program, especially when you're working with coroutines. So we can just see what happens here. So okay, the main function creates a map. Great, and then runs this increment function 1000 times, sleeps for 1 second, and prints the value. So as you all know, what is really this line? If we write this out more explicitly, it will be like this. Plus 1. And now it's more clear to see that when you're incrementing this, if you read the old value here, then obviously the value will be not correct. So if multiple processes are executing this at the same time, you risk that you will have a inconsistent value. So if we just check that we execute it, we should give the same result. But what if we remove these logs? Now I assume that it will give us different answer. Oh, okay. It even fails. It tells us the map doesn't allow this. It detects an error. But let's if we say that okay, we just want to see what will happen. We can use this counter. So now we will just try to implement 1000 times. And then we can print this value. So 930, okay, what happens next time? Okay, somehow it's deterministic. Oh no, here it's different result. A different result. So this is why you should do locking, and the great thing is that it's very simple to do. You just import this sync library, and you call view.lock and unlock. And yeah, here you see that they use the differ files. So what's the typical pattern is that you will just call this unlock immediately with the defer. Yeah. All right. Let's see what's more. Okay, we can skip the exercise. Yeah, so that's it for the Go. If there's any questions regarding this, regarding Go, regarding programming, we can take it now. And if not, we will continue next Monday. And remember, tomorrow it will be lab as usual. And, yeah. Okay. You yeah. Well, it's kind of nice without questions also, but feel free to ask if there's something. Anyway, if there's nothing, then let's just end here and continue on Monday. Yeah. Okay. Oh, bye-bye. Is your screen? Yeah. Yeah, I will share my. I will share like a video of the